Hello students, welcome to this lecture 1 class 10 mathematics, and here in this lecture basically we'll discuss about real numbers. Okay, so before starting chapter 1 real numbers, here first we'll discuss weightage of the syllabus according to CBSE board and the marks or weightage of the marks. Okay, so here we will discuss in this course. Okay, so first we'll discuss number systems. Basically in this chapter, in this units, we will cover real numbers. Okay, and the weightage of this chapter is 6 marks according to CBSE board. Okay, and then second unit is algebra. So in algebra, here we'll cover polynomials, pair of linear equation in two variables, and quadratic equations and arithmetic progressions. Okay, and the weightage of this chapter according to CBSE board is 20 marks, and this chapter is very important. This unit is very important for your CBSE board exam. Okay, so here this is the highest weightage units, algebra. Okay, so in algebra, here basically we'll learn polynomials, pair of linear equations into variables, and quadratic equations and arithmetic progressions. Okay, and then we'll discuss coordinate geometry. So in coordinate geometry, basically we will discuss actually how to represent a order pair, one Cartesian plane. Okay, and we also discuss about Cartesian plane and rectangular coordinate. Okay, coordinate system. And the weightage of this chapter according to CBSE board is 6 marks. Then we will discuss geometry units. Okay, so in geometry we basically will discuss triangles, circles. Okay, so you all know this shape is triangles. Okay, and this shape is circle. So in details we'll discuss we'll discuss about triangles and circles in our upcoming lectures. Okay, so the weightage of these chapters are 15 marks according to CBSE board. Okay, then we will discuss the most important topic, trigonometry. Okay, so basically here we'll discuss introduction to geometry. Okay, and then some application of trigonometry. Introduction to trigonometry, then some application of trigonometry, and the weightage of this chapter is 12 marks. Okay, and then we'll discuss mensuration. Basically in this chapter, in this unit, we will cover areas related to circles, surface areas and volumes. Okay, and the weightage of this chapter is 10 marks. And then we will discuss statistics and probability. Okay, so in our last units we'll discuss statistics and probability, and this unit is also a very important units for all of you. Okay, so the weightage of this chapter is 11 marks according to CBSE board. Okay, so now start real numbers chapter. Okay, so first we discuss here which types of question will come in your exam. Okay, so in your exam, definition based questions may be asked. Okay, so for example, in your exam may ask you in your paper defining rational number, irrational number, prime numbers, composite numbers, and etc. This type of definition based questions may be asked in your board exam. Okay, and the second type of questions, that is theoretical explanation. Okay, so suppose you will give you some statement of a theorem. Okay, then we'll have to give proof of that statement. Okay, such as explaining the fundamental theorem of arithmetic, okay, Euclid's division lemma, or the process of finding HCF, that is highest common factor, and the least common multiples, LCM. Okay, so the theoretical explanation may be asked in your board exam. Okay, and third type of questions where will ask in your question papers, proving numbers to be rational number or irrational number. Okay, so according this chapter, so from this chapter, basically three types of questions may ask in your question paper. Okay, first is definition based questions, second is theoretical explanation, and third is proving a number to be rational or irrational. Okay, so proving numbers to be rationals or irrationals, for instance, proving root 2, root 3, or the sum or product of rational and irrational number is a rational number or irrational number, that may be asked in your question paper. Okay, so now start. So in this lecture, basically we'll cover first recall whatever we have learned in our class 9th, that will I here recall you first. Okay, then we'll discuss Euclid division lemma, this lemma, Euclid division algorithm. So this algorithm is very important algorithm. Okay, and then we'll discuss the fundamental theorem of arithmetic. Okay, and then we'll solve some examples, and then we'll give you an important note. Okay, so let's get started. First, recall. So student, you all know what are composite numbers. So composite numbers, so there are basically two types of numbers. Okay, first is composite numbers and second is prime numbers. So first here I will discuss about composite numbers. Okay, so what are composite numbers? Okay, so composite numbers have more than two positive divisors. Okay, so divisors means if we take this number 4, then the divisors are basically 1, 2 and 3. So 1, 2 and 4. Okay, these three numbers are the divisors of 4. Okay, so composite numbers have more than two positive divisors. Okay, in other words, besides being divisible by 1 and themselves, okay, that is, they have at least one more divisors that also divides the composite number. Okay, so for example, 4 is divisible by 4, D is divisible by 1 to 4. Okay, so here besides being divisible by 1 and itself, the 4 has 2 is more divisor. Okay, so 4 is here composite number. Okay, and similarly 6 have the divisors of 6 are 1, 2, 3 and 6. Okay, so 1, 2, 3 and 6, they are divisors of 6. That in other words, 6 is divisible by 1, 2, 3 and 6. Okay, so if you see here 6, okay, so besides being divisible by 1 and itself, 6 has at least more than two divisors. Okay, so at least one more divisor. So 6 is a composite number. Okay, and if we take 8, so 8, what are the divisors of 8? So 1, 2, 4 and 8. So 8 is divisible by 1, 2, 4 and 8. Okay, so the divisors of 8 are 1, 2, 4, 8. Okay, so the divisors of 8 are 1, 2, 4, 8. So here this number 8, besides being divisible by 1 and itself, it has 2 and 4 divisor. Okay, 2 and 4 divisor as a divisor. So 8, this number is a composite number. Okay, so in onwards, composite numbers is nothing but a number which has more than 2 divisors. Besides being divisible by 1 and itself, it has at least 1 other divisors. Okay, so now we'll define prime numbers, prime factors. Okay, so prime factors, before saying about prime factors, first we recall what are prime numbers. Okay, so what are prime numbers? So we have studied what are composite numbers. Okay, so in case of composite numbers, there we have seen a composite number is a number which has more than 2 divisor. Okay, that is, besides divisible by 1 and itself, that number have more than 1 divisor. Okay, but for prime numbers, a number, suppose p greater than 1, is a prime number if p has the divisor 1 and itself. Okay, so when a number has only 2 divisor, 1 and itself, so beside divisible by 1 and itself, there p has no other divisor. Okay, so this type of numbers is called basically prime numbers. Okay, so for example, you can take 2. Okay, so 2. So 2, this number, the divisors are 1 and 2. For this number, divisors are 1 and 2. Okay, so other than 1 and 2, 2 has no other divisor. Okay, so 2 is a prime number. Okay, and if we take 3, so the divisors of 3 are 1 and 3. Okay, so other than 1 and 3, 3 has no other divisor. Okay, so 3 is a prime number. Similarly, 5, this is also a prime number. 7, this is also a prime number. 11, this is also a prime number. Okay, so 2, 3, 5, 7, 11, 13, and dot dot dot. These are all prime numbers. Okay, so in one words, prime numbers nothing but a number which has only 2 divisors. One is 1 and other is itself. Okay, so our prime numbers has only 2 divisors. Okay, so now prime factors of a number. Prime factors of a number are the factors of that number that are prime. Okay, so if we factorize, if we get factors of a number, and if that factors are prime number, then this factor is called prime factor. Okay, so prime factors of a number are the factors of the number that are prime. So to find the prime factors of a number, first you have to break down the number into factors until all you have left are prime numbers. Okay, so for example, you can take 60. Okay, you can take this number 60. So if we now break 60, so 60 can be written as 2 into 30. Okay, and then you can write 30 as 2 times 15. Okay, and 15 can be written as 3 times 5. So here you get the prime factors of 60 are 2, 3, 2, 2, 3, 5. Okay, so 2, 2, 3, 5. These are prime factors of 60. So here often written in exponent form as 60 can be written as exponent form. Okay, in exponent form as 2 to the power 2 into 3 to the power 1 into 5 to the power 1. Okay, so this is basically the prime factorization of the number 60. Okay, basically here we break the number 60 okay, as its prime factors. So we begin with two very important properties of positive integers, namely the Euclid division algorithm and the fundamental theorem of arithmetic. Okay, so here we begin with first the fundamental theorem of arithmetic. Okay. So Euclid division lemma algorithm, as the name suggests, has to do with divisibility of integers. Okay, so this algorithm, as a name suggests, has to do with divisibility of integers, and stated simply, it says any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r that is smaller than b. Okay, so many of you probably recognize this as the usual long division process. Okay, so actually if we have this positive integer a, okay, so if you have positive integer a, so this positive integers can be divided by another positive integer b. Okay, so these positive numbers can be divided by another positive number b. Okay, then here we'll get some quotient and it leaves a remainder r. Okay, so this thing can be written in mathematically as a, this is equal to b times q plus r. Okay, a is equal to bq plus r, where a is a positive integers, okay, and b is another positive integers, and here the positive integer b divides the positive integers a. Okay, and here q is quotient and r is remainder. Okay, r is remainder, and this remainder r is always less than b. So 0 greater than equal to r, strictly less than b. Okay, so it leaves a remainder, and this remainder r always smaller than b. Okay, so we use mainly to compute the HCF up to positive integers. Okay, so first, so how to compute the HCF up to positive integers? You all know about it. Okay, so if we have two positive integers, okay, so then first you have to factors that numbers into prime factors. Okay, and then you will use the method for finding HCF of two positive integers. Okay, so here first we will discuss the fundamental theorem of arithmetic. So in your earlier classes, you have seen that any natural number can be written as a product of its prime factors. Okay, so any natural number can be written as a product of its prime factors. For example, 2, this number 2. So this 2 is actually a prime number, so 2 can be written as 2. And 4 is a natural number, and this number is a composite number actually. Okay, so 4 can be written as 2 into 2, and 253, this number can be written as 11 times 23. and so on. Okay, so you have already studied about this. Any natural number can be written as a product of its prime factors. Okay, so to take any collection of prime numbers, say 2, 3, 7, 11 and 23, and if we multiply some or all of these numbers, allowing them to repeat as many times as we wish, okay, we can produce a large collection of positive integers. In fact, infinitely many. Okay, so let us list a few number. Okay, so if we multiply 7, 11 and 23, so 7 into 11 into 23, this is equal to 1771. Okay, and if we multiply 3 into 7 into 11 into 23, then it will give us 5313. And if we multiply 2, 3, 7, 11, 23, okay, then you will get 10626. Okay, and if we take the power of 2 cube, okay, 2 cube into 3 into 7 cube, then we'll get 8232. And if we multiply 2 square into 3 into 7 into 11 into 23, and it is equal to 21,252. Okay, so basically by these examples, here we actually confirm, if we multiply sum of one these prime numbers 2, 3, 7, 11, 13, 23 dot, then actually we can produce a large collection of positive integers. Okay, so if we can take them, allowing them to repeat as many as we wish, then we'll get a large collection of positive integers. Okay, and there some examples of this statement. Okay, so now, so there are infinitely many primes. Okay, so actually prime numbers is not a finite number. So prime numbers are infinitely many. Okay, so if we combine all these primes in all possible ways, we'll get an infinite collection of numbers. Okay, and all the primes and all possible products of primes. Okay, so the question is, can we produce all the composite numbers this way? Can we produce all the composite numbers in this way? What do you think about it? Okay, and do you think that there may be a composite number which is not the product of powers of primes? Are you thinking about this? If you think about this, then you are thinking in wrong way. Okay, so we can produce all the composite numbers if we take products of prime factors. Okay, so basically this statement, this actually said to us the fundamental theorem of arithmetic. Okay, so before we answer this, let us factorize positive integers. Okay, that is to do the opposite of what we have done so far. Okay, so we are going to use the factor tree with which you are all familiar. Okay, so you are all familiar with factor tree. Now let us take some large number, say 32760. Okay, and then factorize it as shown in this factor tree. So here the large number is 32760. Okay, so this number 32760, this number is divisible by 2. Okay, so if we divide this number by 2, then you will get 16380. Okay, and further, if we divide this number by 2, then you will get 8190. Okay, so the divisors of 32760 are 2 and 16380. Okay, And then the divisors of 16380 are 2 and 8190. Okay. Then the divisors of 8190 are 2 and 4095. Okay. And further, if we find the divisors of 4095, then we'll get 3 and 1365. Okay. And further, we can divide 1365 by 3. Then we'll get the divisors of 1365 are 3 and 455. Okay, and now if we divide 455 by 5, then we'll get the divisors of 455 are 5 and 91. Okay, and further we can divide 91 by 7. Then we'll get the divisors of 91 are 7 and 13. Okay, so the prime factors of 32760 are 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Okay, so 32760. This is basically equal to 2 into 2 into 2 into 3 into 3 into 5 into 7 into 11. Okay, so this is the prime factorization of 32670. So we here factorize 32760 by using factors tree. Okay, so we have factorized 32760 as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Okay, so as a product of primes, that is 32760, this is equal to 2 to the power 3 into 3 to the power 2 into 5 into 7 into 13. Okay, as a product of powers of primes. Okay, so this leads us to conjecture that every composite number can be written as the product of powers of primes. Okay, in fact, this statement is true and is called the fundamental theorem of arithmetic. Okay, because of its basic crucial importance of the study of integers. Okay, so in this theorem, fundamental theorem of arithmetic, actually it's stated to us every composite number can be written as the product of powers of primes. Okay, and this theorem, fundamental theorem of arithmetic, is very important and crucial theorem for study to the study of integers. Okay, so I stop here this lecture. Thank you very much to all of you.